Chapter 19, Part 3. A telescope uses two lenses to enlarge something that's far away. Again, these two lenses are called the objective and the eyepiece. This system takes rays from an object that are far away from the focal point. It creates a real image, that's the orange lines. The orange lines create a real image inside the focal point of the eyepiece. So we have these orange lines creating a real image right here inside of the focal point of the eyepiece. That's the orange lines. Actually, I can trace those out. So these orange lines are creating our real image. That's what we had before, actually. Now, that real image is going to go through this lens, the eyepiece. That's these green lines. These green lines are going to go through the eyepiece. That is what we see. We backtrack that. This should be like a dashed line using our previous notation. We backtrack that green to see an enlarged image. You'll see that with this one, though, it's inverted. Assuming small angles, we can use this representation for the heights. And our magnification, or we can use these reputations for the heights. This gives us a magnification of m is equal to theta e over theta o, which equals negative FO over FE. This is the same logic as we used before. The definition of the angular size of the object over the eyepiece. This uses the same principles as we used before. The magnification of what we see in the eyepiece versus the magnification of what we see in the virtual image. You should also note that if you're using the angle ratio directly, make sure that your angles are in radians. This assumption only works if theta is in radians. If you use theta to find the focal length, that's fine, it can be in degrees, but if you're plugging it in directly to here, make sure you're using radians. Resolution is the ability to distinguish between different objects. Single slit producing a diffraction pattern where we have theta 1 is equal to 1.22 lambda over d. Here, lambda is the wavelength of light, and d is the diameter of the lens. Theta 1 is the angle between the central maximum and the first minima. It's kind of hard to see here, but Yeah, so we've got the central maxima and the first minima. This ties into resolution. If we have two objects that are separated by a distance of theta, so that we have star 1 here, star 2 here, they're separated by a distance of theta. Our measuring device, or our telescope, can only differentiate angles that are so small. If our theta is bigger than theta 1, then we say that the objects are resolvable. We can tell them apart. We can see that they are two distinctly different objects. If the angle between these objects is equal to theta 1, so if it's equal to the distance between that maxima, then we say that the objects are barely resolvable. That kind of looks like this. You can see that there are two things there, but you don't really have much information on either of them. If the distance between the objects is less than theta 1, then the objects are not resolvable. I went with all caps there for some reason, till the end. Not sure what happened there. In a microscope, the resolution distance between two objects is found using d-min, the minimum distance between the objects, equal to 0.61 lambda over n sine phi of the object, or sine phi, if you like to say Greek letters correctly, I guess. Phi O is the angular size of the objective lens. That's this right here. The angular size of the lens. N is the index of refraction of the material between the object and the lens. That is where we are going to stop chapter 19, and I will end this in a different way. Alright, so that is chapter 19, and I will see you in part 4. So that is chapter 19, and I will see you in our 4th installment of Not the Ideal Medium for Teaching Physics. See ya!